After the fifth dodecahedral layer, we reach the maximum nucleosynthesis expansion. But there is still another morphology resulting from the synthesis popcorn. Indeed, instead of starting from a central apex in the form of planar deuterium, which will increase in 5 directions, we will start from the neutron, which will develop in 3 directions. In a first step, the packets of rejected neutrons will associate in the 20 icosahedral directions. We then obtain the first icosahedral layer consisting of 20 times 3 pentagons. With 60 pentagons, it is the neon isomassive icosahedral morphology. Note that, when this nuclide is spread in space, it will associate with an electronic layer that will then shine as neon lamps do. This is why, when the first stars were created in the quasars, the first clouds, laden with native icosahedral neon, show this milky halo appearance. Now, with a broader base, we find the second icosahedral layer. With 20 times 9 pentagons, we obtain the isomassive element 30, that is to say zinc. But this isomass is very fragile and has a very short lifetime. However, it is especially with the third icosahedral layer that we will obtain the heaviest natural elements of the universe. To understand this structure, let us begin by describing the morphological basis. First, we have a group of 3 times 6 pentagons with 3 stabilization pentagons at the junction. Then, each base group is connected to its neighbors by 2 connecting pentagons that they share. And finally, each group has an internal reinforcement of a triple helix. For the whole of the surface we thus obtain a total of 20 times 24 parietal pentagons. That is to say a total of 480 pentagons that give 80 units of electrical charge. We can thus show the global structure by revealing the internal solidification reinforcements. And with these internal reinforcements, it would be an isomass of mercury 180. But this isotope is naturally unstable. In fact, it is necessary to examine, further, the large gaps in this icosahedral morphology. It is then observed that these gaps have a kind of gear jaw, which can maintain a planar deuterium in internal rotation. And this mini-structure creates a kind of highly localized magnetic ball bearing that allows the stability of these rotating planes. As this planar deuterium shows 6 pentagons in the parietal position, it therefore provides 1 electrical charge unit. Therefore, with 12 parietal gaps, we have 12 possibilities of inserting planar deuterium into the icosahedral wall. Under these conditions, the third icosahedral layer can contain 12 elements ranging from mercury to uranium. And since these additions are formed by groups of 6 pentagons, the same constraints of the fourth dodecahedral layer can be found with the elements 43 and 61. That is, element 81, thallium, and element 91, protactinium, are highly unstable. However, element 81 also has a dodecahedral morphology, where it has two stable isotopes. On the other hand, we know that heavy elements ranging from 83 to 92 are radioactive, and that they form disintegration families starting from a relatively stable parent element to finally give a stable isotope of lead. This is why we will now detail these disintegrations again thanks to the pentamorphic method.